Oh, and you should watch and make sure I press record and that there's little audio bars at the bottom of the screen are going. That way we know. Okay, how are the lights? Can you guys see the screen, especially in the back? Is it okay? All right. Well, here we go. So let's talk a little bit about how to represent the structures of organic molecules. The way that we do this is with something called a Lewis structure. And you probably saw that before in general chemistry. They may have been called Lewis dot structures then. And these highlight covalent bonds which involve sharing of electrons. So you've seen and drawn something like that, right? Which shows you two electrons being shared between two hydrogen atoms. That's the hydrogen molecule. By the way, that is an overly simplistic picture. Bonding in hydrogen, we're going to delve deeply into that. But for now, that's fine. In organic chemistry, we generally aren't going to draw the dots. We're going to draw a line for a bond. Okay? So the line between two atoms means two electrons shared in a covalent bond between those atoms, right? What's here is fully equivalent to what's there. All right, are you used to that kind of thing, drawing bonds with a straight line? Okay. So let's make it a little bit more complicated. In general chemistry, you probably drew something like this for methane, CH4, which indicated to you that the carbon in the middle was surrounded by 8 electrons and was sharing 2 with each of the hydrogens. Alternatively, you may have drawn it like this. That's fine too. And each line represents the 2 electrons shared between the carbon in the middle and the hydrogens on the edge. That looking familiar? Okay, here's the new thing. That picture doesn't really do a great job of communicating the 3-dimensional shape of that molecule. So I'm trying to figure out what you guys remember from general chemistry. A carbon surrounded by 4 things based on this idea of valence shell electron pair repulsion should have what geometry? Tetrahedral. Good, we don't need to talk about that. Yes, that is because the electrons are trying to get as far apart as possible, electron repulsion. So to demonstrate tetrahedral geometry in organic chemistry, here's what we will do. You'll draw 2 lines between carbon and hydrogen, and when those lines are straight like that, you communicate that those lines are in the plane of the page, and then we're going to use a wedge, and you can fill it in and make it all the way dark, or you can leave it empty like that. A wedge means that hydrogen is coming out towards you, and a dash means that hydrogen is going back away from you. In a tetrahedral molecule, all of the bond angles are about 109 degrees. Some of you know that it's 109.5, yay for you, but we don't need that many significant figures, okay? To give you a picture of what this actually looks like, we can go to an app that I have that allows you to draw a molecule and see its shape. So there's methane, and there's the tetrahedral shape, and the view that we have over in the notability document, or the where I was drawing, is basically like this. So you got one CH bond straight up in the plane of the page, another off to the right in the plane of the page, then you have one coming out towards you, towards the left, and another going away from you. All right, questions about that representation? You're going to need to get good at visualizing the 3D shapes of molecules via this kind of drawing with dashes and wedges. All right, well, what if the molecule's more complicated than that? So what if the molecule was CH3, CH3? I'll actually draw a line in between the 2 of those. That will be 2 carbons. Both of them are surrounded by 4 things, so they should both be tetrahedral. And so I can draw that like this. Again, you see that each carbon is surrounded by 4 things. It should be tetrahedral, and that's how you represent that geometry. Okay? Questions about that? Easy? Okay? You're like, bring on the hard stuff. Oh, it's coming. Okay, what if it were 3 carbons? What if we did a molecule that was CH3, then CH2, then CH3? As molecules get bigger in organic chemistry, we get lazier. So I could draw this structure as follows, with all the carbons and the hydrogens shown. And this would be one way to draw the correct Lewis structure. However, it is also permissible in organic chemistry to do something called use a skeletal structure, and this starts to save you time. In the skeletal structure, that's it for this molecule. Okay? So notice what we've done. We've omitted all of the carbon-hydrogen bonds. They're still there. We know they're there. It's assumed that you understand that they're there, but we're not drawing them. So that's going to be tricky. You're going to have to remember that. Second, we assume that there is a carbon at every end of a line and at every point where lines join, at every vertex. So looking at this, I know that this is a CH3 group. I know that this is a CH2 group, and I know that this is a CH3 group. I have to remember the hydrogens that are implied but not shown. The rules are that you assume in a skeletal structure that every carbon has the appropriate number of carbon-hydrogen bonds. I'm going to put an asterisk on that statement because there's something else, there's another detail you're going to need to get that right 100% of the time. But for now, in neutral molecules, assume that every carbon has the number of hydrogens that give it a full octet. And so you don't have to draw the carbons, you don't have to draw the hydrogens. By the way, the rules are a little tricky, but you're learning a language here, right? The Lord says in the Doctrine and Covenants that every man and woman are going to hear the gospel in their own language. If you want to speak to organic chemists and demonstrate that you are competent, you have to speak the language of organic chemistry. And so I'm telling you some of the conventions. One thing that's not okay is to draw this. Some people will tell you that it is not okay, but in my dialect of organic chemistry that I speak, that is a major faux pas. You can't do that. If you draw the carbons, if you actually write out C, you must draw the H's. Okay? Another rule for skeletal structures is that you must draw what we will call heteroatoms. What do we mean by that? Well, carbon and hydrogens are sort of the privileged few in organic chemistry. And everything else we have to write out, like nitrogen, oxygen, fluorine, chlorine, sulfur, etc., phosphorus. If there is a heteroatom in a molecule, you actually have to write it out. So, for example, a related molecule, dimethyl ether, is CH3O, CH3, and we can draw that like this. But I have to draw out the oxygen. Another rule is that if the heteroatoms have hydrogens on them, you must draw the hydrogens on the heteroatoms. So as an example of something we learned in section 89 that we are not to imbibe, here is the molecule ethanol, CH3. A little slow on the uptake, guys. Come on, that was funny. Okay. So one of my sons is taken to rating my dad jokes. And one time he's like, that was a 3, Dad. And I said, joke's on you, that's what I'm going for. That is the range of dad jokes. He said, let me revise that. I need a negative number on our scale to rate that particular joke. Anyway, this is ethanol. It is not okay to draw ethanol like this. We're going to put the big ekis on that one, okay? No. All right. So those are Lewis structures. Just to test yourself really quick, I'm going to draw a skeletal structure, and I want you to draw all the carbons and the hydrogens using dashes and wedges, okay? Go for it. All right, take another 20 seconds. Okay, take like 15 seconds to compare with a friend. You were probably doing that anyway. Okay, your 15 seconds are up. A brave soul volunteer to draw with the pencil. Okay. Come on. Brandon's going to draw what he drew. And don't be bashful, it's not going to break. So now you can see why we don't draw all the C's and the H's, because it takes forever to clear the molecules, right? But, good.
Oh gosh.
That's okay, we're not grading on penmanship, so you're
Good.
Nice H's, actually.
Dude, thank you. I appreciate it.
All right, thank you. Let's give Brandon a hand. Okay, so practice that. There's nothing really to it other than to learn the rules and get used to them, okay? Now, we need to talk about when a molecule is has a charge on it. Yes, go ahead.
Are you particular about whether we do both the wedges on the outside or one on the outside, one on the inside?
Yes. So are we particular about where the wedges are? And the answer is yes. The way to know where to draw the wedges is to look where the line, and the dashes is to look where the lines are. If I have these two lines coming together like this, and I imagine them as an arrow, they point in the direction that the wedges should be drawn. So, for example, I would always draw the wedges like this and dashes like this. I would never draw them like this. If you draw them like that, we can pretty well tell what you're talking about, but it actually doesn't show you the real shape of the molecule. Yep.
Is that just like, I'm not taking a nomenclature, but is that just like convention, or is it actually changing?
Well, it reflects if you were to draw it this way, the bond angle that you've just made is not 109 degrees. So it doesn't actually represent tetrahedral geometry. And if you look at what real tetrahedral geometry looks like, if you take any two of those bonds and put them in the plane of the page, the other two are going to be pointing in the other direction.
But if the wedges just signify one going straight out and one going straight back, they be the same.
Yeah, and it's not exactly right straight out. It's straight out but angled towards you. Notice that as we look at this molecule of methane, the hydrogen in the front here is pointed out towards our right and towards us.
Gotcha.
Yeah, so it's not just straight out at you, it's,
I got you.
yeah, okay, good. Others? Yes?
Does the wedge need to be at the angle that it points, or just going in that general direction?
So the wedge needs to be just going in the right direction. We're pretty tolerant of the precise angle. And in fact, it's difficult to draw it realistically. If you look at it, you see that the hydrogen in the front is basically overlapping with the hydrogen in the back, and that's hard to actually represent. So we don't bother. We draw them like, oops, we've done here, kind of offset. Yeah, and that's fine. Yes?
Are you particular about, like, what if the lines are touching and then you draw the C outside of those lines? Or do they need to?
If the lines were touching and you draw the C outside of those lines, no, you would want to do this. Yep. What else? I'm missing anybody? Gotcha. Okay. Let's now talk molecules with charges. And this is part of drawing correct Lewis structures. So, a formal charge. Have you heard about this before? Maybe. It's not that hard. You'll get it pretty quick, and then it'll become instinctive. So, formal charge is basically a way of bookkeeping electrons, keeping track of the electrons in a molecule. Now, all of you are used to the idea of H3O plus, right? This is water with an extra proton. And the way you can tell that it's positively charged, that H3O is positively charged, is if you add up all of the protons in all of the nuclei, hydrogen, hydrogen, and oxygen, and then you add up all the electrons that are present, you come up with one more proton in the molecule than there are electrons, so there should be a positive charge. Now that takes forever to do, and we need something faster, so there's a method called assigning formal charge that will get us to the right answer. So let me show you how we would do this. Let's draw the Lewis structure of H3O plus. Technically, I suppose, if we were going to draw it, we would draw one of the hydrogens as a wedge. We would try to represent its structure as sort of pseudo-tetrahedral or trigonal pyramidal, where this lone pair sort of occupies this position up here, then there's the hydrogen, then this hydrogen's a wedge, and this one's a dash. That's H3O plus. To assign formal charge, you look at each atom in the structure and you do the following calculation. You first write down the number of valence electrons an atom usually has. And you get that from the periodic table, from the column, right? So oxygen is in the 1, 2, 3, 4, 5, 6th column of the periodic table. So oxygen comes with 6 valence electrons. Then we're going to subtract the number of electrons that the atom owns. What do we mean by that? It's a very legalistic definition. An atom owns all of its lone pair electrons and half of its bonded electrons. Those are the ownership rules. We're not talking about anything other than the convention for assigning formal charge. So oxygen here owns 2 electrons from its lone pairs. It owns both electrons in the lone pair. And then it's involved in 3 bonds, and it owns half of the electrons in each of those bonds. So that's 3, 4, and 5. Oxygen owns 5 electrons. Got it? So the formal charge on oxygen is +1. And we will draw the structure of hydronium with a plus charge on next to the oxygen. Okay? To have a correct Lewis structure, you must draw the correct formal charge on every atom that has a non-zero charge. Yeah?
I've also seen it drawn where there's square brackets around the whole Lewis dot structure and then a plus. Would that work too, or just?
So if you do the square bracket around the whole Lewis structure, that's technically correct. It tells you the thing is positively charged. It doesn't assign formal charges to each of the atoms. I won't really give you that option on an exam. I'll draw a molecule, I'll point an arrow, and you'll have to answer A, B, or C. What's the formal charge on the molecule, on the atom? Yeah.
So because it has a formal charge of +1 on the oxygen, is it fair to say that that extra proton is in that section of the molecule?
Right. So this is an interesting question. Because the formal charge is on the oxygen, is it correct to say that that's where the plus charge is, that the missing proton is felt mostly there? And the answer is no. It turns out formal charge is only about bookkeeping. It sometimes gives you insight into where, what parts of the molecule are electron rich and other parts that are electron poor. Other times it doesn't. You're going to have to use principles of electronegativity to help you out. For example, in this specific case with hydronium, the formal charge tells me that the oxygen has a plus formal charge. By the way, what's the formal charge on hydrogen? Just do the math. Hydrogen comes with 1 electron. It currently owns how many? Just 1, so 0, right? So if you were to try to interpret formal charge as anything other than bookkeeping, you might be led to an incorrect conclusion. What do you know about the electronegativity of oxygen? More or less than hydrogen? More, right? So that tells you that even though the positive formal charge is on oxygen, the actual location of that plus charge is probably spread out onto the hydrogens. That the hydrogens are electron poor. Most of the time, we're just going to assume that you know that. We'll talk about that in chapter 2. You'll learn to develop that part of your OChem thinking. If we want to highlight that in a drawing, one of the things we can do is put a little bit of delta plus. That is the lowercase Greek letter delta, and in front of a plus, that indicates a partial positive charge on the hydrogens, which would tell you that the hydrogens are electron poor, whereas the oxygen is electron rich, even though the oxygen's got a positive formal charge, okay? So we use formal charge to give us a sense, to make sure we know exactly what's going on in the molecule. We know that the molecule itself is positively charged. We use formal charge for bookkeeping purposes, but then when we go to talk about reactivity, we also have to add in everything else we know about electronegativity. Other questions there? So let's do some more formal charge practice. You'll get chances to do this. Again, it's not that hard if you follow the rules. So let's do a molecule with a nitrogen on it. This molecule happens to be called an imine. You won't learn about those until 352. So what is the formal charge on the nitrogen? Nitrogen normally comes with how many valence electrons? 5. And then how many does it currently own? 5. You can tell it owns both of the electrons in the lone pair, and then 1, 2, 3 bonds. You count each bond, right? So currently owns 5, so nitrogen's formal charge is 0, okay? Now, what about all of the carbons and the hydrogens in the imine? Hydrogen should be 0, right? Because hydrogen has normally 1 valence electron. It currently owns 1, so formal charge is 0. What about the carbon? Also 0, because carbon comes with 4, currently bonded to 4, owns 4 of those electrons, so the formal charge is 0. Okay, so you're going to start to notice patterns that are going to help you out. A carbon bonded to 4 things is always going to have 0 formal charge. A nitrogen involved in 3 bonds is always going to have a 0 formal charge. Let's do another nitrogen-based compound. Let's do this one, which is a household cleaning chemical, ammonium hydroxide, or ammonium. We'll just draw this positively charged one. And I already gave you this, dang, it's so ingrained in my habits that I couldn't not draw the charge. So you already know the answer. Nitrogen has a positive formal charge. How can you tell that's the case? Well, again, nitrogen has 5 valence electrons. It currently owns only 4. 1, 2, 3, 4. And therefore, its formal charge is +1. Let's do some others. Let's do this molecule. And I will draw in the lone pairs for you. Tell me what the formal charge is on that oxygen. Valence electrons, oxygen normally has 6. It currently owns, 2, 4, 6, and then half of the electrons in its bonds, 7. So that's -1. So you'll get used to seeing that an oxygen bound to only one thing has a negative formal charge on it. And in this case, that actually does tell you where the reactive portion of the molecule is. In that case, the negative formal charge on the oxygen aligns with what you know about oxygen's electronegativity. And you would expect that oxygen to be very electron rich. Okay, just a few more to get used to some things that you're going to see in organic chemistry. Let's do a molecule that has a double bond in it. What's the formal charge on that carbon? 0, right? Okay, great. No other explanation needed there. What is the formal charge on this oxygen?
0.
Good. How about this one? Good, okay, great. Let me draw for you now another molecule, BH3. Boron is weird, right? Boron normally has 3 valence electrons. It currently owns 1, 2, 3. There's no lone pair on the boron. If there were, I would have drawn it for you. So the formal charge on boron is 0. Boron is an example of something that's neutral when it doesn't have a full octet. It's only surrounded by 6 electrons. What if I change the molecule and go like this? What is the formal charge on that boron? 3 minus 4 equals -1, so you'd put a negative charge there. Okay, and then here's one. What about this molecule, CH3, and there's no lone pair on the carbon? +1, right? Carbon normally has 4, currently only owns 3, so it's +1. This type of molecule is called a carbocation, and we'll learn more about those structures later. Okay, practice that. It's not hard, but you need to do a few examples to make sure you can get it right every time. Okay, In the last little bit, we need to talk about a concept called resonance. So you've heard about it before, and it was probably, it's possible, in fact likely, that you have some misconceptions about resonance that we need to clear up. Resonance is one of the fundamental concepts in organic chemistry. If you get it, a lot will be easier. If you don't, let's just say there's a particular test problem that students get wrong again and again and again if they don't master this. So save yourself some trouble. Let's start with actually this molecule that we did up here. The molecule that has two oxygens, one's involved in a double bond and one isn't. Okay, resonance, and we'll put the negative formal charge on the oxygen where it's negative, where we decided the formal charge is. Resonance is a situation in which, without moving the atoms, you can have an alternative arrangement of electrons. That is a different Lewis structure. And usually, you're only moving, and by moving I mean to get from one resonance structure to another. I'm going to have more to say about that concept of moving. Generally, you're only moving lone pairs and electrons in what I'm going to call a pi bond. That language doesn't make sense yet. It will in a moment. Notice, or it will probably next time. Notice that this oxygen is involved in two bonds to carbon. They call that a double bond, and that's fine. But typically in organic chemistry, we think of a double bond as actually being two separate bonds. One is called a sigma bond. That is the Greek letter sigma. And that isn't because it's so awesome. Is that how you guys use the term? I never really understood that. But it relates to the orbital symmetry that makes the bond. And we'll talk about that in a little bit. The second bond is a pi bond. That's the Greek letter pi. Okay? So when I say electrons, lone pairs and electrons that are in a pi bond, and in a Lewis structure, you can't really tell which one is sigma and which one is pi. You just know that one is one and the other is the other. We're going to be, in making resonance structures, we're going to be moving lone pairs and sigma bonds. So an alternative resonance structure for this molecule would be for me to draw all of the atoms in the same place and all of the sigma bonds in the same place, but for me to now put the double bond here and me to now put a lone pair over on the other oxygen. The way that I convert one resonance structure into another is with the lone pair pi bond two-step. And this is something that can occur anytime a lone pair is adjacent to a pi bond. I take an arrow, I start with the lone pair, and I move it. I point the arrow to the space between the oxygen and the adjacent atom. That tells me that I am taking the lone pair and moving it over to form a pi bond. If I stopped there, I would have too many bonds to carbon. One of the rules of Lewis structures is no more than 8 electrons can be around a second row element. So if I stop there, I'd have 5 bonds to carbon, and that's not okay. So I have to break the other pi bond and move it out to its adjacent atom, the oxygen. So that's the two-step arrow sequence that allows you to convert one electron to another. That's resonance. As an exercise, I want you to work on this problem for next time. I'm going to draw a molecule that's somewhat unusual. It's got a lone pair here with a negative formal charge, and I want you to draw the other resonance structure using this same method. We'll have more to say about resonance next time, and then we're going to return to a more full picture of covalent bonding. Yeah?
Well, I've also seen these structures drawn with the dotted line.
Yeah, I'll say more about that next time. Sometimes you've seen people draw resonance structures with dotted lines. I'll tell you what we're talking about there. Okay, stay tuned. I'll let you know when the course is published, when you have access to the syllabus and the study guide and so on. I'll see you Friday.